Hey there, I wanted to show you the next step in number systems, which is understanding hexadecimal numbers, or, excuse me while I get that, base 16, which is called hexadecimal. So if we've so far learned base 2 and base 10 number systems, I want to explain how this one works, and it really works exactly the same way. The first thing you have to do, and you can see this over here in this chart, you can ignore most of this, but if you look over on that side, if you have base 16, that means you have to have 16 different digits or symbols for the numbers. And so this is easy up to a point, right? Because we understand the numbers 0 through 9 pretty well. But this literally, and this is the part that makes people go, whoa, is that they need to come up with a symbol for a single, like a single symbol that they've never used before for the number 10. Because we can't reuse, like in base 10, we can start reusing the ones and the zeros. We can't do that. We need to make 16 different digits. And so far, we started at 0, we've gotten through 9, and then what do we do for 10? So in hexadecimal, they've decided that A equals 10, B equals 11, and so on and so forth. F equals 15. Remember, you never do 16 because it starts at 0. So it goes 0 to 15, and that's 16 digits altogether. So that's the first thing that makes people confused. But let's just say that we have let's do a 3-digit base 16 number. So let's just randomly pick 491, or what we would read as 491. And we say that this is in base 16. The question is, how do we understand base 16 and how do we convert that to base 10? And the answer is exactly the same way as we would in any other number system, which means that this is 1 times 16 to the 0th power. This is 9 times 16 to the 1st power, and this is 4 times 16 to the 2nd power. So remember, we always do this. This is how bases work. It's why we call it the base. We take each digit, we multiply it by the base, and then we put that base to a different exponent, right? So this is the same thing as saying 1 times 1, because anything to the 0th power is 1, so that is value of 1. 9 times 16, okay? Well, if you have your calculator, you can take that out, and you could try to figure it out faster than me. I get 144. I should probably get out my calculator and double check that. And 4 times 16 squared. So what's 16 squared? 256 times 4 is 4, 22, 8, 9, 10. It's 1024. Now, it's just a coincidence that the ones I'm choosing happen to have all these 4s in it. So we have to add all that up together. In other words, we have to add 145 to this, so we get 9611. So 491 in base 16 equals 1169 in base 10. So it's the same kind of conversions. It's just changing the base. And another project you're going to do soon is going to be something similar, where I say take any base. Just think of a base off the top of your head. You should be able to do the same kind of math to convert, because that's how it goes. Now, the good news in base 16 is, first of all, like, why base 16? Why, of all the different bases you might be able to think of, did I choose base 16? And the answer is a little math thing for you. 16 squared equals 2 to the 8th. These numbers are exactly the same. Actually, I'm going to switch colors here. This is 256, 16 squared. 2 to the 8th is 256. Why is that significant? Because 2 to the 8th equals 1 byte of data. So, in the end, what you need to know is that instead of writing a byte of data, like if I wanted to write the number 255, I would have to write 1, I'm just going to do it this way, 1, 1, 1, 1, 1, 1, 1, 1 equals 255. Remember, it starts counting at 0, goes to 255, and so we can fit 256 pieces of information in this. So that's a byte. That was like if every single value on a byte has been turned on. There's 8, 0, 1, 2, 3, 4, 5, 6, 7, 8, 2 to the 8th power. But we can do the same thing here. All we have to do, though, is make it represent, all we need is 2 digits. Instead of 8 different digits to show a byte, which gets really long, we can use 2 digits to show a byte. And so what am I saying? I am saying that all in the end, hexadecimal is handy for computers because it's a shortcut. We can represent big numbers in less space when we use base 16 instead of using base 2. So really, we don't even care that much about base 10 anymore. We care about the fact that these two are so compatible with each other that it makes a really nice system. In other words, let's just say that you are a coder and you needed to write something in binary. Why represent it with a whole bunch of zeros and ones when you can represent it with just a few digits in base 16? So there's these things, IP addresses, or there's things called MAC addresses. There's all these various things that go on inside the computer, and they all have like these long strings of numbers, and I'm just making them up, but it's like, you know, if you go into something like this, and then you're like, oh, this is hexadecimal. Well, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits of hexadecimal, which is the same thing as like 8 times 10, 80 digits of binary numbers of zeros and ones. So imagine writing 80 zeros and ones, and it's like, no, instead of doing that, let's just write it like this. Saves a lot of space. It looks confusing because it's got these letters in it. So remember, these letters mean numbers. So in the end, here's what you need to know. That's all the theory. Remember, I always give the theory, and then I'm going to tell you the easy part. And so this is the easy part. Base 16 is a shortcut to base 2. And if I was to give you, every time I talk about base 16, I'm going to give you a chart. This is why this chart now is up here. It's because I'm going to give you a chart that looks like this. And in fact, I'm just going to fill in some zeros over here. Because I want to show you that every single number here now is a 4-digit number in binary. And so watch this. I can take any number I can think of in binary. 1, 1, 0, 1, 0, 1, 1, 0. And here's a byte, right? So if I list a byte, and I divide that byte in half, I can now take my chart, and I can look up this byte over there. So where is that? 0, 1, 1, 0. 0, 1, 1, 0, that was 6. So I'm going to write 6. And now, 1, 1, 0, 1. 1, 1, 0, 1. That's the number 13. But in this, we call it D. And so, 1, 1, 0, 1, 0, 1, 1, 0 equals D6 in base 16. So here's the binary. Here's the base 16. So another thing to know about that is if I was to say, hey, what's D6? What's this equal in base 10? Like, how do we understand this in decimals? And so then you could say to yourself, oh, Well, I can do two things. I can do 6 times 1 and d, which is 13, 13 times 16. And I can add these things up. Because remember, this is 16 to the 0th, which is 1. And this is 16 to the first power, which is 16. And so I can say 6 plus whatever 13 times 16 is. But I don't want to do all that. I am just going to go back over to my binary and go 1, 2, 4, 8, 16, 32, 64, 128. And I am going to add 6 and 128, 64, and 16. 128, 64, 16. It's 12 plus 6 is 8. And 8, 9, 10, 208. So 208 plus the 6 is 214. So this binary equals this base 16 equals this base 10. And I didn't have to do all this. Like, okay, yeah, this would have been 208 if I had done it. And I would have said, oh, look, that's 214. So I could have done it either way. But because we're probably good at the binary way, all you need to know is if I convert my binary, I can then easily use my chart. I can do the same thing going backwards. So I'm just going to choose some random number, 173. I'm going to choose that in base 10. And now I'm going to convert, and I'm going to do it slightly different than I did before with the dividing. I'm going to try something different. How many 128s are there in 173? There are 1. What's the what's left over after I do that? So 13 minus 1, this is a 5. I had to borrow, so that's 45. Okay, so there's 45 left. So how many 64s are there? 0. How many 32s? 1. 32, 3, 13 left. How many, let's see, this was 128, this was 64, this was 32. So now down to 16, there's 0 16s. How many 8s are in there? Oops. How many 8s are in there? 1. Now I'm down to 5. How many 4s? 1. I'm down to 1. How many 2s? 0. How many 1s? 1. And so 173 is 10101101 in base 2. Now I divide it in half, and I go 1010. A. 1101. D. So 173 in base 10 is 10101101 in base 2. And is AD in base 16. And so the chart saves me all the work. As long as I can still do binary and decimal conversions, I can quickly get to the base 16. The base 16 is actually the easiest part of the whole thing, if you have the chart, and you always will have the chart in the various quizzes or assignments that I give you to do. So that's base 16 in a nutshell. It might not be easy. I went kind of fast on some of my conversions, so watch this a few times if you need to get extra help or to kind of see what happened, or look at the notes because maybe you can't read the board that well from where you are, and the notes will help as well. But I hope my explanation out loud at least helped a little bit. Good luck.